Now, the issue with quarter wave transformer is that we need some theoretical uh, uh, characteristic impedance wires that we don't have, and we only have standard characteristic impedances. So instead, what we're going to be using is the same wire that we have used here. But instead of quarter wavelength transformer, what we're going to be doing is actually to just put some more wire over here. This is what we call a stub. Alright, so what we're doing is stub matching, specifically series stub matching, specifically series short stub matching. So we're going to be changing the impedance of this. Now this only works if the characteristic impedance has its real part be equal to the load impedance, its real part is equal to the characteristic impedance. So for example, this is 20 ohms. This has to be like 20 plus jx ohms. If this doesn't match, you have to do some more calculations. Essentially just moving this stub over somewhere else. But for now, for the simpler calculations, we will just take a look over here. Now, this stub actually looks something like that. And if we look at here, for example, this is R and this is R plus JX. When we look at here, I want our Z in, looking at the load, to be R instead of R plus JX. So what we're going to do is the input impedance of the stub itself, the Z in stub, is going to be negating this reactive part. So it's going to be negative JX. Alright? So that's going to be our goal. Now, for the formula. Now, since this is a short, the formula for the input impedance of a shorted trans line is ZO or JZO tangent beta S, right? The ZO we will set as the same as earlier, and beta is 360 over lambda. S is what we want, alright? So S, what is S? First of all, we need to divide Z in stub by JZO. So Z in stub over JZO. And if we actually do this, with purely imaginary Z in stub, for example, negative JX, the J's here would cancel each other out, leaving us with real. If we did this with a complex J, it would not exist because tangent of a complex number is a bit complicated. And if we do that, we need the arctangent now. So arctangent of Z in stub over JZO. And then we need to divide by beta. Again, beta is 360 degrees over lambda. So that's the first formula for a series shorted stub matching. Now, what about a stub that is open? So it's essentially just two wires. Well, for a series open stub matching, the formula for an open trans line or an infinite load is ZO over J tangent beta S. Again, we want the S in here. So we just take the reciprocals. So tangent beta S in here. Sorry, this one. Tangent beta S would be equal to ZO over Z in stub. And then we would have to find the arctangent of that. So let's rearrange. and then we have to divide by 1 over beta as usual. So the difference is that the, oh hang on, the j is missing. There you go. So jz in stub in the denominator. So it's just this and that got switched over. Everything else looks the same. So this is a series stub matching. Now again, it only works if the real part of the load impedance is the same as the real part in here. Otherwise, if this is different, we have to move it somewhere else, which is a bit more difficult, and that's going to be included with the method for actually doing this, which is this Smith chart.